Hello to everyone. In this session, we have to discuss about P series. Here, the series of the form summation 1 by n raised to p is equal to 1 by 1 raised to p plus 1 by 2 raised to p plus 1 by 3 raised to p up to plus 1 by n raised to p is called the P series. Theorem: the P series summation 1 by n raised to p is convergent if p greater than 1 and it is divergent if p less than or is equal to 1. Proof of this theorem: case A, let p greater than 1. Now, so in the P series we consider the first term 1 by 1 raised to p is equal to 1 if p greater than 1. That implies 1 by 2 raised to p plus 1 by 3 raised to p less than 1 by 2 raised to p plus 1 by 2 raised to p. So that this is less than less than 1 by 2 by 2 raised to p less than, so 2 by 2 raised to p can be written as 1 by 2 raised to p minus 1. Similarly, consider 1 by 4 raised to p plus up to 1 by 7 raised to p. So this is less than 1 by 4 raised to p plus 1 by 4 raised to p plus 1 by 4 raised to p plus 1 by 4 raised to p. So this is less than, this is 4 times, so 4 by 4 raised to p. So that can be written as less than 1 by 4 raised to p minus 1. So that is also can be written as less than 1 by 2 raised to p minus 1 whole square. Similarly, we have to take 8 terms. So we get 8 by less than 8 by 8 raised to p, that is less than 1 by 2 raised to p minus 1 whole cube. Now consider summation 1 by n raised to p is equal to 1 by 1 raised to p, 1 by 2 raised to p up to plus 1 by n raised to p. So this can be written as, so first term is 1 by 1 raised to p, then you combine 2 terms, then you combine 4 times, then 8 terms, like that. So 1 by 1, you know that 1 by 1 raised to p is 1, already we find that one. Next, this can be written as 1 by 2 raised to p minus 1, and this can be written as 1 by 2 raised to p minus 1 whole square, and this can be written as 1 by 2 raised to p minus 1 whole cube. Clearly, this series is geometry series with common ratio 1 by 2 raised to p minus 1. So here, if p greater than 1, then the common ratio 1 by 2 raised to p minus 1 less than 1. So that means the above geometric series is convergent. So therefore the series summation 1 by n raised to p is convergent if p greater than 1. In case B, so here we have to take p is equal to 1. So then the P series is 1 by n raised to p is equal to summation 1 by n raised to, so here p is equal to 1, so series becomes 1 by n raised to 1, that is 1 by n, that is equal to 1 plus 1 by 2, 1 by 3 up to plus 1 by n. So next here 1 plus half is equal to 1 plus half, then 1 by 3 plus 1 by 4 is greater than 1 by 4 plus 1 by 4. So 1 by 4 plus 1 by 4 is 2 by 4, that is half. Similarly, in next step you have to consider 4 terms, so that is also equal to half. So that means summation 1 by n is greater than 1 plus half plus half plus half. Here this is also geometric series with common ratio 1. Next, Sn is equal to half plus half up to n terms. So that means Sn is equal to n times half. So apply the limit on both sides. Limit of Sn as n tends to infinity is equal to limit of n into half as n tends to infinity. So this is equal to infinity. That means Sn is divergent. Therefore, the series summation 1 by n is also divergent if p is equal to 1. In case 3c, we have p less than 1. So now p less than 1, that implies n raised to p less than n. So that implies 1 by reciprocal of that 1, that means 1 by n raised to p greater than 1 by n. Then by the second comparison test, summation 1 by n raised to p diverges when p less than 1. So this is the proof of p series. Then we have one more theorem. So that is statement is, let summation an and summation bn be the two series of positive terms, and limit of an by bn as n tends to infinity is equal to 0. Then we have to prove that if summation bn is convergent, then summation an is also convergent. And the second one is, if summation bn is divergent, then summation an is need not be divergent. So proof of this theorem. First case, here in statement the given limit of an by bn as n tends to infinity is equal to 0. Then by the definition of limit of the sequence, we have there exists epsilon greater than 0, there exists m belongs to n such that modulus of an by bn minus 0 less than epsilon for all n greater than m. So that means an by bn lies in between minus epsilon and 0. So for all n greater than m. So that implies that can be written as an by bn less than epsilon for all n greater than m. So next, that means an less than epsilon into bn. So since here bn is convergent, by first comparison test summation an is also convergent. For second one, we prove this case with an example. So consider the series summation an, that is equal to summation 1 by n square, and summation bn is equal to 1 by n. Now an by bn is equal to 1 by n square 1 by n. So that is equal to 1 by n. Then apply the limit on both sides as n tends to infinity. So we get limit of an by bn as n tends to infinity is equal to 0. So hence summation bn is divergent, whereas summation an is convergent as p greater than 1 in summation 1 by n raised to p. So we have one important note. So that is, to find the nature of the series summation an, we must find auxiliary series summation bn. whose nature is known and limit of an by bn as n tends to infinity is equal to L. So that is not is equal to 0. So here we have a useful note to find the bn. So that is bn is equal to highest degree term only of an in numerator divided by highest degree term only of an in denominator. So revision of this session is here we have discussed on P series, and these are the reference books for this session. So thank you one and all. Thank you very much.